Hello there, and welcome back to the Sleepy Universe channel. I'm glad you found your way here tonight. Maybe the day has felt a little heavy. Maybe your thoughts are still moving in circles, even though the room around you has already gone still. Or maybe you're simply the kind of person who likes falling asleep to the oldest mysteries in the universe, where the mind can wander without needing to hurry anywhere at all. Either way, you are in exactly the right place. There's nothing you need to solve right now. Nothing you need to finish. Nothing you need to prove. You can let your shoulders soften. Let your jaw unclench. Let your breathing become a little slower, a little deeper, a little quieter. And if your thoughts are still busy, that's all right too. You don't need to push them away. You can just let them drift beside the sound of this voice, like faint particles floating through a shaft of distant starlight. Tonight, we are going somewhere dark, but not in any frightening way. We're traveling toward one of the strangest and most beautiful ideas in all of science. We're going to spend some time with black holes. Black holes have become symbols of mystery. They live in the imagination as invisible mouths in space, places where stars disappear, and time itself begins to behave differently. They bend light, they distort distance, they shape galaxies, and they sit at the edge of our understanding of gravity, quantum mechanics, and the structure of the cosmos. They sound dramatic, and in some ways they are. But seen from far away and listened to slowly, they are also calm. They are quiet expressions of nature, following its deepest rules. Tonight, we'll move through 100 gentle facts about black holes. We'll begin with what they really are and what they are not. Then we'll drift through their birth in the collapse of massive stars, through the giant black holes that live in the centers of galaxies, through warped time, curved light, invisible boundaries, glowing disks, powerful jets, gravitational waves, and the far future of a universe where even black holes may one day fade. Some of these facts may sound almost like myths, a place where escape becomes impossible, a darkness that can outshine a galaxy, a border that has no surface and yet changes everything, a region where time passes differently than it does here on Earth. But all of this comes from the patient work of observation, measurement, mathematics, and imagination guided by evidence. The universe is under no obligation to feel ordinary. Often, the deeper we look, the more gently strange it becomes. And just before we begin, if these calm cosmic explorations help you unwind, relax, or drift off a little more peacefully at the end of the day, consider liking and subscribing to the channel. It helps other sleepy minds find their way here too, one quiet orbit at a time. Now, let the room grow softer around you. Let the day rest at the edge of your awareness. And let's begin. 1. A black hole is not really a hole in the usual sense. It is not an empty tunnel cut through space, and it is not a doorway punched into the fabric of the universe. A black hole is a region where matter has been compressed so intensely that gravity becomes overwhelming. Once something passes a certain boundary around it, called the event horizon, there is no path outward that leads back to the wider universe. The word hole survives mostly because the effect feels so absolute. Things can go in, but nothing that crosses that border can come back out. It is less like a hole in cloth and more like a steepness in reality itself, a place where the shape of space and time turns inward. Even from the first fact, black holes begin by asking us to imagine differently. 2. What makes a black hole so powerful is not some mysterious new force, but gravity following Einstein's theory of general relativity to an extreme conclusion. Mass tells space and time how to curve, and curved space and time tell matter and light how to move. In the case of a black hole, that curvature becomes so deep that every possible future direction points inward once the event horizon is crossed. That means light is not being grabbed like a fish in a net. It is still trying to travel naturally through the geometry around it. But the geometry has become too severe. The roads all lead down. In that way, a black hole is not merely an object. It is a landscape, one so bent that escape ceases to be part of its map. 3. The event horizon is the most famous feature of a black hole, and also one of the easiest to misunderstand. It is not a glowing shell, not a solid wall, and not a visible surface floating in space. It is a mathematical boundary that marks the point of no return. If you remain outside it, escape is still possible. If you cross it, every path available to you leads deeper inward. What makes this boundary feel so eerie is how ordinary it can seem from the outside. In some situations, especially around a very large black hole, there may be no local signpost announcing that you have arrived, no line painted across space, no sudden sound, just a quiet crossing from one kind of future into another. 4. Black holes can be incredibly massive without being very large in diameter. A stellar black hole might contain 10 times the mass of the Sun and yet fit inside a sphere only a few dozen kilometers across. That is a huge amount of matter compressed into a very small region, far beyond the densities we encounter in everyday life. This extreme compactness is part of what makes black holes so difficult to imagine. We are used to mass being spread out in objects with familiar textures and surfaces. But in a black hole, the mass is concentrated to such a degree that ordinary intuition stops being useful. It is one more reminder that the universe is not limited by the scales that feel comfortable to human minds. 5. Despite their dramatic reputation, black holes do not suck in everything around them the way vacuum cleaners suck dust from a floor. This is one of the most common misconceptions, and it comes partly from the name. If you are far enough away, a black hole pulls gravitationally just like any other object with the same mass. Its influence depends on distance, just as the gravity of stars and planets does. If the Sun were somehow replaced by a black hole with the exact same mass, Earth would continue orbiting almost exactly as it does now. We would lose sunlight and warmth, which would be catastrophic for life, but not because the orbit itself had suddenly changed. Gravity would remain the same at Earth's distance. Black holes are extreme, but they still obey the logic of mass and distance. 6. Most of the stellar black holes we know about are thought to form when very massive stars reach the end of their lives. During a star's lifetime, the outward pressure from nuclear fusion balances the inward pull of gravity. But when the fuel begins to run out, that balance fails. The star can no longer support its own weight in the same way, and the core begins to collapse. In some cases, that collapse ends in a neutron star. In others, if the remaining core is massive enough, gravity wins so completely that no known force can stop the inward fall. The star leaves behind a black hole, a remnant darker than anything it once shone upon. A brilliant life can end as a silence so deep it changes the structure of space itself. 7. Not every star is heavy enough to become a black hole. Smaller stars, including stars more like our Sun, follow a different path. They eventually swell into red giants, shed outer layers, and leave behind white dwarfs, which are dense but still supported against further collapse. Some heavier stars leave neutron stars instead. Tiny objects so dense that a spoonful would outweigh a mountain. Only the most massive stellar cores can collapse far enough to form black holes. So black holes are not the default ending for all stars. They belong to a more selective and dramatic branch of stellar death, one reserved for the giants. Even among stars, there are different ways to leave the stage. 8. Astronomers think some black holes form in the aftermath of supernova explosions, where a star ends its life in a violent outburst that briefly rivals the light of an entire galaxy. But not all black hole births may be accompanied by such fireworks. In some cases, a star may collapse more directly, with little or no bright explosion visible from afar. This quieter path is sometimes called direct collapse. The star simply gives way under its own gravity and vanishes into a black hole with minimal outward display. It is an oddly gentle idea for such an extreme event, as though a star could spend millions of years shining only to conclude its life by falling inward in near silence. 9. The black holes formed from collapsing stars are called stellar mass black holes. Their masses usually range from a few times the mass of the Sun up to dozens of solar masses, and sometimes more in special cases. Even at the lower end of that range, they are extraordinary. A few suns' worth of mass confined to a region the size of a city is enough to create staggering gravitational effects. These are the black holes often found in binary systems, where they orbit with companion stars and sometimes feed on stolen gas. They are, in a sense, the most personal black holes to us, because they are born from stars not unlike those scattered throughout our own galaxy. Cosmic mystery often begins with familiar ingredients, taken to unfamiliar limits. 10. Between stellar black holes and the enormous giants found in galactic centers, astronomers suspect there is a middle category called intermediate mass black holes. These objects would be heavier than the remnants of single stars, but much smaller than supermassive black holes. For a long time, they were elusive, almost like a missing chapter in the cosmic story. Finding them is difficult because they are neither common enough nor dramatic enough to reveal themselves easily. But over time, more evidence has begun to suggest that they do exist, perhaps in dense star clusters or unusual energetic systems. The universe often resists tidy categories at first, revealing its in-between forms only after years of patient looking. 11. At the far grander end of the scale are supermassive black holes, the giants that live in the centers of most large galaxies. These black holes can contain millions or even billions of times the mass of the Sun. They are not simply scaled-up versions of stellar black holes in a casual sense. Their sizes, growth histories, and environments place them at the heart of some of the largest structures we know. Our own Milky Way contains one. So does the Andromeda Galaxy. So do many others scattered across the universe. It is a quietly astonishing thought that galaxies, those great spirals and ellipticals of stars and dust, often have a dark center around which much of their long history unfolds. 12. The supermassive black hole at the center of the Milky Way is called Sagittarius A star. Usually written Sagittarius A star and spoken as Sagittarius A star. It lies about 26,000 light-years from Earth, hidden behind clouds of dust that block much of the visible light from the galactic center. though invisible to ordinary sight. Its mass has been measured to be roughly 4 million times that of the Sun. That mass is packed into a region smaller than our solar system. The stars near the center of the galaxy race around it at extraordinary speeds, tracing the presence of something compact, dark, and immensely heavy. In this way, Sagittarius A star became known long before it was ever imaged. It revealed itself by how others had to move around it. 13. Another famous supermassive black hole sits at the center of the giant galaxy M87. This one is far larger than Sagittarius A star, containing billions of solar masses. It became the first black hole ever imaged by humanity in a direct and historic way. The image did not show the black hole as a bright body, but as a dark center surrounded by a glowing ring of hot material. Released in 2019, that image became one of the defining scientific pictures of the modern era. It was not just beautiful. It was also a profound confirmation that the equations describing black holes correspond to something the universe truly builds. A shadow in light became a proof in the sky. 14. The first image of Sagittarius. A star itself was released later, in 2022. It was more difficult to capture than the image of M87's black hole, even though Sagittarius A star is much closer to us. The reason is that the gas around it changes more quickly, making the image blur and shift over short timescales. It is like trying to photograph a candle flame through moving air. Still, with enough observations and careful reconstruction, astronomers were able to reveal its shadow too. For those who study black holes, it was a deeply satisfying moment. The quiet center of our own galaxy, hidden for so long behind dust and mathematics, finally took on a visible shape in human history. 15. The dark central region seen in black hole images is often described as the black hole's shadow. This shadow is not the event horizon itself, but a larger feature created by the bending of light. Photons passing near the black hole are redirected, trapped, or sent on looping paths, creating a dark silhouette against the brighter glow of surrounding gas. So what we see is not light coming from the black hole, but a pattern formed by light that could not escape. Light that was bent away, and light emitted by nearby matter. In a beautiful sense, the black hole becomes visible through the behavior of what surrounds it, that is seen by the absence it creates. 16. Black holes do not emit light of their own, but matter falling toward them often does. As gas and dust spiral inward, they form an accretion disk, a flattened structure of orbiting material. Within that disk, friction, compression, and magnetic turbulence heat the matter to enormous temperatures, causing it to glow in visible light, ultraviolet light, X-rays, and other wavelengths. This means the darkest object in a system can become associated with some of the brightest radiation in the universe. The black hole itself remains silent, but the material approaching it can shine intensely. It is one of the most striking paradoxes of astronomy. Darkness can be wrapped in light. 17. Accretion disks form because matter falling inward usually has some sideways motion or angular momentum. Instead of dropping straight in, the material begins to orbit, colliding with itself, flattening into a disk, and slowly spiraling toward the black hole as it loses energy. This process is both orderly and chaotic, a kind of cosmic whirlpool governed by physics rather than water. The disk can become incredibly hot near the center, where orbital speeds are highest and gravity is strongest. The closer the gas gets, the more energy can be released. In that narrow, bright region around a dark core, some of the most efficient energy conversion in the universe takes place. 18. Quasars are among the brightest known objects in the universe, and they are powered by actively feeding supermassive black holes. When a huge black hole at a galaxy's center is swallowing large amounts of gas, the accretion disk can radiate so intensely that it outshines the galaxy's stars. From billions of light years away, that brilliant beacon can still be detected. So when we look at a quasar, we are not seeing the black hole directly. We are seeing matter heated to extraordinary brightness as it falls inward. In this way, black holes announce themselves not by their own glow, but by the transformation they impose on the matter around them. The invisible makes the visible blaze. 19. Some quasars are so distant that their light began traveling toward us when the universe was very young. This means supermassive black holes already existed not long after the first generations of stars and galaxies began to form. Their early appearance is one of the great puzzles in astronomy, because growing a black hole to billions of solar masses takes time. How did they get so large so quickly? Perhaps the earliest black holes had unusually massive seeds. Perhaps the young universe allowed gas to fall inward more efficiently than it does today. Or perhaps several growth mechanisms work together. The question remains open, and like many of the best questions, it leaves room for wonder. 20. One idea for creating large, early black hole seeds is direct collapse on a much bigger scale than the death of a single star. In this scenario, a vast cloud of gas in the early universe might collapse almost all at once, without first fragmenting into ordinary stars. The result could be a much larger black hole from the beginning, giving cosmic growth a head start. This possibility is still being investigated, but it helps explain how the universe might build giants quickly. Sometimes the challenge is not in understanding how something grows, but in understanding how it begins. Black holes remind us that origins can be as mysterious as endings. 21. Black holes can spin, and many of them do. This spin is a fundamental property, along with mass and, in principle, electric charge. A rotating black hole changes the structure of space-time around it in important ways. It does not simply sit there like a motionless pit. It twists the geometry nearby, influencing how matter and light behave close to the event horizon. The idea that a dark object can rotate so quickly that it drags space and time with it feels almost unreal. But it comes directly from Einstein's equations. Rotation adds texture to the mystery. A black hole is not always a still point. It can be a deep, turning well in the fabric of the cosmos. 22. The dragging of space-time by a rotating black hole is known as frame dragging. In ordinary life, space feels like a quiet stage on which things move. But near a spinning black hole, the stage itself is being twisted. Objects and light close enough to the black hole are compelled to move in the direction of that spin. This effect is subtle around Earth and other familiar objects. But near black holes, it becomes profound. It means that motion itself is partly rewritten by the rotation of mass. In the neighborhoods of black holes, even the idea of standing still becomes more complicated than we are used to. 23. Outside the event horizon of a rotating black hole lies a region called the ergosphere. In this zone, frame dragging is so strong that nothing can remain at rest relative to a distant observer. Everything must move in the direction of the black hole's rotation. It is a strange and elegant region, one that exists because spin reshapes what space-time allows. The ergosphere has fascinated physicists because, in theory, it may allow energy to be extracted from a black hole's rotation. That possibility sounds almost magical, but it emerges from the geometry itself. Even black holes, which seem like ultimate endings, can in some contexts become sources of outward power. 24. The theoretical process for extracting energy from a rotating black hole is called the Penrose process. It involves splitting an object inside the ergosphere so that one part falls inward and the other escapes with more energy than the original object had before entering. The extra energy comes from the black hole's spin, which is slightly reduced in the process. This is not something we know how to do as a practical engineering project, of course. But it is a wonderful example of how richly surprising general relativity can be. A black hole does not merely consume. Under the right theoretical circumstances, it can also give a little of its rotational energy back to the universe. 25. One of the most famous consequences of strong gravity near a black hole is time dilation. According to general relativity, clocks run more slowly in stronger gravitational fields compared with clocks farther away. Near a black hole, this effect can become dramatic. For someone watching from a safe distance, processes near the event horizon appear stretched out in time. This does not mean time stops for the person close to the black hole. Locally, their own clock still feels normal. But when their experience is compared to someone far away, the difference becomes enormous. Black holes remind us that time is not one universal river flowing equally for everyone. It is part of the landscape shaped by gravity. 26. To a distant observer, an object falling toward a black hole appears to slow down as it approaches the event horizon. The light from the object becomes more red-shifted, weaker, and delayed. It seems to linger near the edge, fading gradually rather than crossing cleanly. From afar, the boundary looks almost like a place where motion itself is stretched into stillness. But for the falling object, the experience is different. It crosses the event horizon in a finite amount of its own proper time. There is no endless suspension from that point of view. This difference in perspective is one of the reasons black holes feel so deeply strange. Reality is not contradictory there, but it is more relative than intuition expects. 27. Black holes also bend light from other objects, acting as gravitational lenses. If a star or galaxy lies behind a black hole from our point of view, the black hole's gravity can distort, magnify, or redirect the light coming from that background source. Sometimes this creates arcs, rings, or temporary brightening effects that reveal the presence of an otherwise hidden mass. This means a black hole can be discovered by what it does to distant light, rather than by anything it emits. The universe is full of these indirect revelations. Things that cannot be seen plainly still leave signatures in motion, in timing, in brightness, and in geometry. Black holes are masters of that kind of quiet evidence. 28. Around a non-rotating black hole, there is a region called the photon sphere, where light can orbit in unstable paths. This does not mean there is a safe ring where beams of light circle forever in perfect peace. The orbits there are delicate and unstable, so even a tiny disturbance can send light either away into space or inward toward the black hole. Still, the idea is astonishing. Light, which we usually imagine traveling in straight lines unless something reflects or refracts it, can be bent into loops by gravity alone. Near black holes, the universe becomes a place where paths that seem impossible from ordinary experience become part of the local architecture. 29. Tidal forces near black holes can become extreme. Tidal force is the difference in gravity between one part of an object and another. If one side of your body is much closer to a black hole than the other, the nearer side feels a much stronger pull. The result is stretching along one direction and compression along another. This process is often described with the playful term spaghettification, because an object can be pulled into a long, thin shape. The name sounds almost humorous, but the physics behind it is severe. Even so, its existence tells us something elegant. Gravity is not just a pull. It also has texture across space. 30. The intensity of tidal forces at the event horizon depends on the black hole's size. For smaller stellar mass black holes, those forces can become destructive before you even cross the horizon. But for a very large supermassive black hole, the event horizon can be comparatively gentle at the moment of crossing because the curvature is spread over a larger region. That means a person falling toward a huge black hole might cross the event horizon without immediate catastrophe, at least initially. The deeper consequences would still come later, but the boundary itself need not feel dramatic at the local scale. Once again, black holes resist the simple expectations created by their name. 31. At the center of a classical black hole, general relativity predicts a singularity, a place where density and curvature become infinite. Most physicists suspect that this prediction signals the breakdown of the theory, rather than a literal infinity in nature. When equations produce infinities, it often means the description is incomplete at those scales. So the singularity is both a prediction and a warning. It tells us where our current understanding reaches its limit. Somewhere in that extreme interior, gravity and quantum mechanics must meet in a deeper framework that we do not yet possess. Black holes are not only cosmic objects, they are invitations to better theories. 32. This is part of why black holes are so important in modern physics. They sit at the crossroads of general relativity, which describes gravity and large-scale structure, and quantum mechanics, which governs the very small. Each theory works extraordinarily well in its own domain, but black holes force them into conversation under the most extreme circumstances. Where they agree, we learn something profound. Where they strain against each other, we discover where our knowledge is unfinished. In that way, black holes are not just interesting astronomical phenomena. They are laboratories of thought, places where the universe presses on the edges of our best ideas. 33. In the 1970s, Stephen Hawking made one of the most famous discoveries related to black holes. By combining insights from quantum theory and curved spacetime, he showed that black holes should not be perfectly black. Instead, they should emit a faint thermal radiation, now called Hawking radiation, because of quantum effects near the event horizon. This was a stunning result. It meant that black holes could slowly lose energy and mass over time. Something we once imagined as permanent and absolute turned out to be more subtle. Even a black hole, under the long patience of the universe, may eventually fade. 34. Hawking radiation is extremely weak for astrophysical black holes, which is why we have not detected it directly from the kinds of black holes found in the sky. For stellar mass and supermassive black holes, the temperature associated with Hawking radiation is far colder than the cosmic microwave background that fills the universe. In practical terms, these black holes absorb far more energy than they emit. So while Hawking radiation is theoretically profound, it does not cause ordinary black holes to evaporate quickly. The process is unimaginably slow. If black holes are patient objects in general, then through Hawking evaporation, they become patient almost beyond language itself. 35. A stellar black hole would take vastly longer than the present age of the universe to evaporate completely through Hawking radiation. A supermassive black hole would take even more time, an amount so huge that all familiar cosmic eras would pass long before its final fading. Galaxies would change, stars would die, and still the black hole would remain. This makes black holes important in thinking about the far future of the cosmos. They may outlast the brilliant things that created them. In the very long arc of time, darkness may prove more durable than light. It is a quiet inversion of what feels true in everyday life. 36. Black holes also have entropy, a fact that transformed theoretical physics. Entropy is often associated with disorder or the number of microscopic arrangements consistent with a system's overall state. For black holes, the entropy turns out to be proportional not to the volume inside them, but to the area of their event horizon. That relationship is deeply strange and deeply important. It hints that information, gravity, and geometry may be linked in ways we are only beginning to understand. A surface can encode something about a volume. A boundary can hold a hidden richness. Black holes continue to teach physics by refusing to behave in ordinary ways. 37. The idea that black hole entropy scales with area helped inspire the holographic principle, a bold concept suggesting that information about a region of space might be describable in terms of data on its boundary. This is still a subtle and developing area of theoretical physics, but black holes played a major role in opening that door. It is remarkable that an object famous for swallowing information became central to some of our most ambitious ideas about how information is stored in the universe. Black holes do not simply consume old concepts. They give birth to new ones. 38. This leads to the black hole information paradox, one of the deepest unresolved problems in theoretical physics. If something falls into a black hole and the black hole eventually evaporates, what happens to the information about what fell in? Quantum mechanics strongly suggests that information cannot simply vanish from reality, yet classical black hole descriptions seem to heed it completely. Over the decades, physicists have proposed many possible resolutions. Perhaps the information is encoded in subtle correlations in the radiation. Perhaps the event horizon is more complicated than it appears. Perhaps a deeper theory changes the question entirely. The debate continues, and black holes remain at the center of it, quiet but insistent. 39. Another famous phrase associated with black holes is that black holes have no hair. This does not refer to anything literal, of course. It means that a simple black hole can be fully described by only a few basic properties, especially mass, spin, and electric charge. The complex details of what formed it are not preserved in any obvious outward way. A collapsing star, a cloud of matter, or something stranger may all produce black holes that look the same from the outside if those few properties match. It is a startling compression of history. The universe can sometimes reduce a complicated story to a very simple ending. 40. In practice, astrophysical black holes are expected to have almost no net electric charge, because any excess charge would attract opposite charges from the surrounding environment and quickly neutralize. That means the two most important properties for real black holes are usually mass and spin. Even with only those two, however, their behavior can be richly varied. The simplicity of the black hole itself contrasts with the complexity of its surroundings. Disks glow, jets erupt, stars orbit, gas falls, magnetic fields twist. The central object may be elegantly minimal, while the region around it becomes one of the most dynamic environments in the cosmos. 41. One of the main ways astronomers discover stellar black holes is through X-ray binary systems. In these systems, a black hole orbits a normal star. If the star's outer gas drifts too close, the black hole's gravity can pull that material away. The stolen gas forms an accretion disk, heats up dramatically, and emits powerful X-rays before crossing the event horizon. The black hole itself remains dark, but the process of feeding turns its surroundings into a beacon. These systems are like nighttime lanterns for invisible objects. By studying the X-rays and the motion of the companion star, astronomers can infer the presence of a black hole even when they cannot see it directly. 42. Cygnus X1 was one of the earliest and most famous black hole candidates. It was discovered as a strong X-ray source and later studied in detail as part of a binary system. The visible companion star's motion showed that the unseen object was too massive to be a neutron star. A black hole became the most compelling explanation. For many people, Cygnus X1 was the moment black holes stopped being purely theoretical curiosities and began to feel like real inhabitants of the sky. Science often moves this way. An idea lives in mathematics, then in suspicion, then in evidence, and finally in the quiet confidence of repeated observation. 43. Other X-ray binary systems have deepened our understanding of black holes by showing how accretion changes over time. Some systems brighten suddenly in outbursts when large amounts of gas fall inward, then fade again. Others remain comparatively steady. By watching these cycles, astronomers learn how disks form, wobble, heat, and sometimes become unstable. The result is a kind of weather map for gravity at the edge of darkness. Black holes may not emit light themselves, but the matter around them can live through states, flares, transitions, and rhythms. Even invisible objects can have luminous seasons. 44. Astronomers can also identify black holes by tracking the motion of visible stars around an unseen companion. If a star appears to orbit empty space, and the mass required to explain that orbit is too large for a neutron star or white dwarf, a black hole becomes the best interpretation. In these cases, gravity serves as the signature. This method has been especially powerful in the center of the Milky Way. There, by watching individual stars move over many years, scientists were able to map the invisible mass at the galactic center with extraordinary precision. The stars became tracers, drawing the outline of darkness. 45. One of the most famous of those stars is called S2. It follows a tight, elongated orbit around Sagittarius A star and moves at enormous speed when it swings close to the galactic center. Observing S2 over time provided some of the clearest evidence that a compact, supermassive object sits there, exerting gravitational control over the region. In addition, S2's motion has allowed astronomers to test aspects of general relativity in the strong gravitational field near a black hole. So the star is not just a witness. It is also a tool, a moving clock and marker whose path reveals the geometry of the space it travels through. 46. Some black holes are active and easy to detect because they are feeding. Others are quiet. A black hole with no nearby companion star and little gas around it may emit almost nothing at all. Such an object can drift through space nearly unnoticed, betraying itself only through subtle gravitational effects. This means the universe may contain many more black holes than we have directly identified. A large hidden population may move through galaxies in silence. Not every important object shines. Some simply bend the paths of others and continue on in darkness. 47. Astronomers suspect that many rogue black holes may wander through the Milky Way without belonging to any bright system. Some may have formed in binaries and then been flung away. Others may be the remnants of stars whose surroundings offer no convenient light source for detection. These black holes would travel alone, carrying gravity but not glow. It is a strangely peaceful image. Dark remnants crossing the galaxy for millions of years, passing star fields and gas clouds unseen, disturbing almost nothing. Space is vast enough to make even dramatic objects seem quiet. A black hole in solitude becomes almost meditative. 48. One way to find isolated black holes is through gravitational microlensing. If a black hole passes between us and a more distant star, its gravity can focus and magnify the star's light for a while. The star brightens in a particular way, even though the lens itself remains invisible. By analyzing the event carefully, astronomers can estimate the mass of the hidden object. Microlensing is a beautiful method because it depends on geometry, timing, and patience rather than brightness. It allows darkness to be found through the brief rearrangement of light. Sometimes the universe lets us see the unseen only indirectly, in passing, like a shape noticed by how it alters a shadow. 49. The direct detection of gravitational waves in 2015 opened an entirely new way of studying black holes. When two black holes orbit one another, they gradually lose energy by emitting ripples in space-time. Their orbit shrinks, they spiral closer, and eventually they merge. The waves from that final collision travel outward across the universe at the speed of light. When instruments on Earth detected those waves for the first time, it marked a historic turning point. Humanity had, in a sense, learned to hear the universe through space-time itself. Black holes that emitted little or no light could now announce their existence in a new language. 50. The signal from a merging pair of black holes is often described as a chirp because its frequency and amplitude rise rapidly as the objects spiral together. Faster orbit means stronger and quicker waves, building to a final peak at merger. Though we cannot hear gravitational waves directly with our ears, scientists can translate the signal into sound. The resulting chirp is brief, but it carries extraordinary information. From it, researchers can estimate the masses of the black holes, their spins, their distance from Earth, and details about the final object left behind. A tiny vibration in space-time becomes a story of enormous mass in motion. 51. Black hole mergers can release an astonishing amount of energy in gravitational waves. In some events, several times the mass of the Sun is converted directly into wave energy in a fraction of a second. The power output during that brief moment can exceed the combined light of all the stars in the observable universe, even though almost none of it appears as visible radiation. This is one of those facts that strains the imagination. Something dark and silent, far away, emits a burst of sheer gravitational power so vast that ordinary comparisons feel fragile. Yet the event leaves the night sky visually unchanged to our eyes. The universe is busy in ways daylight never suggests. 52. After two black holes merge, the newly formed black hole can receive a recoil kick. This happens because the gravitational waves emitted during the merger may not be perfectly symmetrical. If more wave momentum goes in one direction, the final black hole is pushed in the opposite direction, sometimes at significant speed. In extreme cases, this kick could send a merged black hole far from its original location, perhaps even out of a small galaxy. So black holes are not always fixed in place. Even they can be launched by the imbalance of space-time ripples, as though gravity itself had nudged them onward. 53. Some astronomers think repeated mergers may help build larger black holes in dense environments such as globular clusters or galactic centers. In these places, many compact objects can gather in a relatively small volume, increasing the chance of encounters and collisions over long periods of time. A black hole formed in one merger might later merge again. This process is sometimes called hierarchical growth. It suggests that black holes can have layered histories, built not from one dramatic event alone, but from a chain of unions spread across ages. Even darkness may have ancestry. 54. Globular clusters, which are dense spherical collections of old stars, have become important places to search for intermediate mass black holes. If one of these clusters contains a hidden central black hole, the motions of stars near its core may reveal it. But the evidence can be subtle and difficult to interpret, because many stars packed together create complex gravitational behavior. Still, the search continues because clusters are natural places to ask whether repeated interactions can build something larger than a stellar remnant. Sometimes, a long-lived system becomes a workshop where gravity slowly assembles new possibilities. 55. Supermassive black holes and their host galaxies seem to be connected in surprisingly intimate ways. The mass of a galaxy's central black hole often correlates with properties of the galaxy's bulge, such as the motions of stars there. This suggests that the growth of the black hole and the growth of the galaxy are linked over cosmic time. Exactly how that relationship works is still being studied. Does the black hole help regulate the galaxy? Does the galaxy's structure feed the black hole? Probably both. In astronomy, the largest systems often evolve together, each shaping the conditions of the other in slow, mutual conversation. 56. Active black holes can influence star formation in their host galaxies through a process known as feedback. When a supermassive black hole is feeding strongly, its radiation, winds, and jets can heat surrounding gas or push it away. Since stars form from cool, dense gas, disrupting that gas can reduce future star birth. In this way, a black hole can act as a kind of hidden governor on a galaxy's development. The dark center helps decide how bright the rest may become. It is a subtle but profound role, one that turns black holes from local oddities into architects of galactic history. 57. Jets from supermassive black holes can extend for astonishing distances, sometimes far beyond the visible body of the host galaxy. These jets are narrow streams of energetic particles launched from the vicinity of the black hole, often close to the speed of light. They are shaped by magnetic fields, rotation, and the violent conditions in the inner accretion flow. Seen across space, they can look like beams drawn with impossible patience. A tiny central region can influence matter across hundreds of thousands of light years. Black holes teach scale in a peculiar way. A small heart can move an enormous body. 58. In clusters of galaxies, jets from central black holes can inject energy into the hot gas between galaxies, preventing it from cooling too quickly. This matters because cooling gas tends to fall inward and form stars. By reheating or stirring that gas, the black hole helps shape the long-term evolution of entire galactic environments. So the influence of black holes is not limited to their immediate surroundings. Their feedback can ripple upward in scale, affecting clusters, gas reservoirs, and cosmic structure. The darkest centers often have the widest reach. 59. A black hole that feeds at a high rate can generate powerful outflows of gas as well as jets. These winds can sweep through the host galaxy, carrying energy and momentum outward. In some cases, they may clear away the material that was feeding the black hole in the first place, leading to a kind of self-regulating cycle. This is one reason active galaxies can change over time. A black hole may flare brightly for a while, then fade as fuel becomes scarce or is pushed away. Growth and restraint are woven together. Even cosmic appetite has limits set by its own consequences. 60. Near some black holes, astronomers infer the presence of a hot corona above the accretion disk. This corona is made of extremely energetic particles and emits X-rays. Exactly how the corona forms and behaves is still an active area of research, but it appears to be a crucial part of the environment around feeding black holes. The corona adds another layer to the system. Disk below, black hole within, hot energetic cloud above, magnetic fields threading through everything. The region around a black hole is not simple emptiness. It is a complicated engine, luminous and dynamic at the edge of darkness. 61. The inner edge of an accretion disk depends in part on the black hole's spin. For a rotating black hole, stable orbits can exist closer to the event horizon than they can around a non-rotating one. This means matter can fall deeper into the gravitational well before crossing the horizon, releasing more energy along the way. By studying the radiation from the inner disk, astronomers can estimate how fast some black holes spin. So spin is not just a theoretical detail. It becomes something written into the light of infalling matter, a hidden property that careful observation can decode. 62. The innermost stable circular orbit, often shortened to ISCO, marks the smallest orbit where matter can circle a black hole without rapidly plunging inward. Inside that radius, stable circular motion is no longer possible, and the final inward fall begins. The location of the ISCO depends on the black hole's spin and the direction of the orbit. This creates a natural boundary in the structure of the accretion disk. Matter can orbit, radiate, and linger outside it. But within it, the inward journey accelerates. Even near chaos, black holes maintain precise thresholds and transitions. 63. Accretion does not always happen quietly or at the same rate. Some black holes feed slowly for long periods. Others experience dramatic surges. In certain cases, the inflow can become thick, turbulent, and so luminous that radiation pressure plays a major role in shaping the disk. The behavior depends on fuel supply, magnetic conditions, and many interacting processes. This variability is part of what makes black holes so interesting to observe over time. they are not frozen symbols. They are systems that change, flicker, brighten, dim, and reorganize themselves. Even silence in the universe can have weather. 64. There is a concept called the Eddington limit, which describes a balance point where the outward pressure from radiation can counteract the inward pull of gravity on infalling material. If an accreting black hole shines too brightly, that radiation can make it harder for additional gas to fall in. In simple terms, feeding creates light, and too much light can resist more feeding. Yet the universe often finds ways around simple limits. Under some conditions, black holes may accrete material at rates that effectively exceed this balance for a time. Once again, nature follows rules, but the details of how those rules are expressed can be wonderfully intricate. 65. Some of the most dramatic black hole systems are blazars, which are active galaxies whose jets happen to point almost directly toward Earth. Because of this orientation, the jet's emission is strongly boosted in our direction, making the galaxy appear especially bright and variable. We are seeing not a different kind of engine, but a different viewing angle. This is a good reminder that astronomy depends heavily on perspective. The universe is the same, but what it looks like can change enormously depending on how it is oriented relative to us. Black holes are masters of this lesson. Geometry matters almost as much as gravity. 66. Orientation also helps explain why some active galactic nuclei appear obscured. Dusty structures around the central black hole can block direct views of the innermost region from certain angles, while other angles provide a clearer line of sight. So two galaxies with similar central engines may look very different simply because we are viewing them from different directions. This idea helped unify several categories of active galaxies under a common framework. Sometimes apparent differences in nature are really differences in vantage point. The cosmos is full of objects that become simpler once perspective is understood. 67. The Event Horizon Telescope, which captured the first black hole images, is not a single telescope in one location. It is a global network of radio observatories spread across Earth, coordinated so precisely that they act together like one planet-sized instrument. This technique is called Very Long Baseline Interferometry. No single dish could have achieved the necessary resolution on its own. To glimpse the shadow of a black hole, humanity had to turn much of the planet into a shared eye. There is something beautiful about that. To see darkness clearly, cooperation had to span the Earth. 68. The data gathered by the Event Horizon Telescope are so large and so detailed that hard drives have had to be physically transported between observatories and processing centers. In some cases, this was faster or more practical than sending everything over the internet. The image of a black hole was not one snapshot, but the result of patient assembly from many places. Science can sometimes look instantaneous from the outside when a result is announced, but inside it is often a story of clocks, cables, calibration, weather, algorithms, and enormous care. Even the most dramatic cosmic image can begin with people patiently handling drives full of numbers. 69. Later observations of black holes have included polarization measurements, which help reveal the structure of magnetic fields near the event horizon. Light becomes polarized when its waves align in particular ways, and this can carry information about the environment through which it was emitted or scattered. Around black holes, polarization offers clues to the magnetic order within the glowing plasma. These details matter because magnetic fields may help launch jets and shape the motion of infalling matter. So even the light around a black hole can arrive with hidden layers of information, like a whisper carrying more than one message at once. 70. Computer simulations are essential in black hole astronomy because the environments around black holes are too extreme and too distant to experiment with directly. Researchers simulate the behavior of hot plasma, curved spacetime, magnetic turbulence, radiation, and relativistic motion. Then compare the results with observations. In this way, theory and data meet in a careful dance. The images we see are not simply photographs in the everyday sense. They are interpretations grounded in physics, informed by models, and checked against signals from the sky. Understanding black holes requires both looking and imagining with discipline. 71. Some simulations suggest that in certain black hole systems, the magnetic field near the event horizon can become so strong that it partially chokes the inflow of gas. These are called magnetically arrested disks. In such cases, the magnetic field itself becomes a dominant player in the flow, storing and redirecting energy. This is another reminder that black holes are not isolated in their effects. Matter, radiation, and magnetic structure all interact in complex ways. The central gravity may set the stage, but the performance involves many actors. 72. Not all black hole mergers are expected to produce visible light. If two isolated black holes spiral together in emptiness, the event may release gravitational waves without any significant electromagnetic glow. The universe contains collisions that are physically enormous, yet visually silent, detectable only through the trembling of space-time. This silence is part of what makes gravitational wave astronomy so transformative. It reveals events that would otherwise remain hidden forever. A new sense expands the world. The dark becomes audible. 73. In some environments, however, black hole mergers might occur within gas-rich regions, such as dense disks around supermassive black holes. If so, the collision could disturb the surrounding matter and perhaps generate a flash or flare of light in addition to gravitational waves. These possible mixed signals are of great interest because they would let astronomers study the same event in multiple ways. When the universe offers more than one messenger, understanding deepens. Light tells one part of the story. Waves in space-time tell another. Together, they create a richer portrait of what happened in places no human will ever visit. 74. Future gravitational wave observatories, including space-based missions, are expected to open up new black hole populations. A mission like LISA, for example, is designed to detect lower-frequency gravitational waves than ground-based detectors can easily observe. That means it could study massive black hole binaries and other slow, large-scale systems in ways we cannot yet do. In a sense, we are still at the beginning of listening. The first detections were only the start of a new branch of astronomy. Black holes will likely be among its greatest storytellers. 75. Some black hole binaries may spend long ages slowly spiraling together before their final merger. During that time, they orbit one another in a hidden dance, gradually giving up energy through gravitational waves. The final collision may be brief, but the prelude can last millions or billions of years. This is common in the cosmos. The dramatic moment that captures our attention is often preceded by a long preparation invisible to us. A flash, a merger, a burst, a chirp. behind each may lie an ancient and patient approach. 76. Black holes can also form from the collapse of very massive stars in environments with low amounts of heavy elements. Such stars may lose less mass through stellar winds before death, leaving behind larger cores that are more likely to produce heavier black holes. This helps explain why some gravitational wave events have involved unexpectedly massive stellar black holes. The chemistry of a star's environment can therefore influence the kind of black hole it becomes. Even in death, stars remember something about where they were born. The universe writes history into matter long before gravity closes the final chapter. 77. The first generation of stars in the universe, often called population 3 stars, may have been particularly massive. If so, some of them could have left behind early black holes that later helped seed larger structures. We have not observed these first stars directly, but their legacy may survive in the black holes they created and in the chemical enrichment of later galaxies. This is one of the gentle beauties of astronomy. We often learn about vanished things through what they left behind. A first star may be gone, but its death can still echo through cosmic history. 78. There is also the speculative idea of primordial black holes, which would not form from stars at all. Instead, they would arise from unusually dense regions in the very early universe, perhaps fractions of a second after the Big Bang. If such regions collapsed under their own gravity, they might create black holes of many possible masses. Primordial black holes have not been confirmed, but they remain interesting because they would connect black hole physics to the earliest conditions of the cosmos. They would be fossils from a time before stars, before galaxies, before ordinary structure had fully formed. 79. Some physicists have even considered whether primordial black holes could account for a portion of dark matter. This possibility is constrained by many observations and remains uncertain, but it shows how black holes reach into other great mysteries of cosmology. They are never content to stay in one chapter of science for long. Whether or not primordial black holes contribute meaningfully to dark matter, the idea has been fruitful. It encourages observations, predictions, and new ways of testing the early universe. Even unconfirmed possibilities can help science move. 80. The density associated with a black hole does not always behave the way intuition suggests. A supermassive black hole has a much larger event horizon than a stellar mass black hole. And if you average its mass over the volume inside that horizon, the resulting average density can actually be lower than that of water for the most gigantic examples. This sounds surprising because black holes are symbols of compression. But it highlights the importance of distinguishing between the nature of the horizon and the unresolved question of the interior. Black holes are full of scale-dependent strangeness. The bigger they become, the more some expectations soften. 81. A very large black hole can therefore have a relatively gentle gravitational gradient at its event horizon compared with a small one. That is why crossing the horizon of a supermassive black hole may not involve immediate tidal destruction, while crossing near a small stellar black hole would be far harsher. Size changes experience in important ways. This means black holes are not all alike in how they would be encountered, at least in thought experiments. The same word describes a family of objects, and within that family there is variation, nuance, and scale. The cosmos likes categories, but it also likes gradients. 82. If you could somehow orbit close to a black hole and survive the environment, the view of the universe would be profoundly distorted. Light from background stars would bend around the black hole, creating warped patterns, multiple images, and rings. The sky itself would seem reshaped by gravity. This is another reason black holes fascinate artists as well as scientists. Their physics naturally produces scenes that feel dreamlike. Yet the dream is disciplined by equations. The strange images are not inventions layered onto the universe. They are what the universe actually allows. 83. Around black holes, relativistic effects can also change the appearance of accretion disks. Material moving toward us can look brighter because of Doppler boosting, while material moving away appears dimmer. This means the glowing ring around a black hole is often uneven in brightness, with one side enhanced by motion. Even light becomes directional in a new way there. Speed, gravity, and geometry all shape what we see. Black holes do not merely bend paths, they sculpt appearances. 84. When a star wanders too close to a supermassive black hole, it can be torn apart in a tidal disruption event. The star is stretched, shredded, and turned into streams of gas. Some of that gas escapes, while some falls inward and produces a luminous flare that can briefly outshine the host galaxy's usual core emission. These events are dramatic, but they are also valuable. They reveal black holes that were previously dormant or difficult to detect. A hidden object suddenly leaves a brilliant signature, as though the galaxy's dark center briefly lifts its veil. 85. Not every tidal encounter leads to total destruction. In some cases, a star may lose only part of its outer layers and survive to return on a later orbit. This creates the possibility of repeating flares or partial disruptions, where the black hole gradually strips the star over time rather than consuming it all at once. There is something haunting in that idea. A star circling too near, shedding brightness and mass in installments. The cosmos has many endings, and some are swift while others arrive in slow pieces. 86. Black holes are often portrayed in science fiction as portals, wormhole engines, or instantaneous routes to elsewhere. Wormholes do arise as mathematical possibilities in certain solutions of general relativity, but no actual wormhole has been observed. Real black holes, as far as we know, are remarkable enough without serving as shortcuts. This is part of their enduring charm. Nature did not need to become less real in order to become more extraordinary. The true black hole, with curved spacetime, slowed time, trapped light, and giant invisible mass, is already more than enough to keep the imagination awake. 87. White holes are another speculative idea sometimes discussed alongside black holes. A white hole would be something like the time-reversed version of a black hole. Matter could come out, but nothing could go in. These objects remain hypothetical, and there is no observational evidence that they exist in the universe around us. Still, the concept reveals how deeply black holes shape theoretical thought. Once you follow the mathematics far enough, new shadows and opposites begin to appear. Whether they are realized in nature is another question. But black holes keep expanding the territory of what physics is willing to contemplate. 88. It is natural to wonder whether a black hole could threaten Earth. On human and even planetary timescales, there is no reason to think a black hole is wandering toward us in a dangerous way. Space is vast, stars are widely separated, and close encounters with black holes are extraordinarily unlikely. The galaxy contains hazards, but it also contains immense room. This is one of the comforting truths of astronomy. The universe can be full of dramatic things without those things being immediate threats. Most of the sky's violence happens very far away, softened by distance into wonder. 89. If Earth did somehow orbit a black hole with the same mass as the Sun at the same distance, the orbital mechanics would remain nearly unchanged. But life as we know it would not survive, because sunlight would be gone. The planet would cool, oceans would freeze at the surface, and the biosphere would collapse or retreat into unusual refuges. This thought experiment is less about danger than about perspective. It shows that black holes are not uniquely destructive at a distance. What matters is mass, heat, light, and environment. A black hole can replace gravity well enough, but it cannot replace the warmth that made us. 90. Some black holes may hide in apparently ordinary star systems, detectable only through tiny wobbles in the visible star's motion. Modern precision measurements of starlight and stellar positions make it possible to search for such subtle gravitational companions. In this way, the census of black holes grows not only through spectacular events, but also through careful bookkeeping. Astronomy often advances through patience. A tiny periodic shift in a star's path can reveal a dark companion weighing several suns. The unnoticed becomes undeniable by repetition. 91. Black holes have helped confirm general relativity under extreme conditions. The motions of stars near Sagittarius. A star, the gravitational waves from mergers, and the images of black hole shadows all provide tests of Einstein's theory, where gravity is especially strong. So far, general relativity has passed these tests impressively well. At the same time, black holes remind us that passing tests is not the same as being final. The theory still encounters puzzles at singularities and in quantum contexts. Success and incompleteness can coexist, and science grows precisely in that tension. 92. Because black holes are so compact and so gravitationally intense, they are among the best natural laboratories for studying how matter behaves at high energies. Gas near them can be heated to enormous temperatures, accelerated to relativistic speeds, and threaded by powerful magnetic fields. Few other places in the universe combine such extremes so efficiently. For scientists, this makes black holes not only mysterious objects, but useful ones. They are sites where nature performs experiments for us, if we are patient enough to learn how to read the results. 93. When astronomers study black holes, they often rely on many wavelengths of light at once: radio, infrared, visible, ultraviolet, X-ray, and gamma ray. Each range reveals different parts of the system. Radio observations may trace jets. X-rays may reveal the hot inner disk or corona. Infrared may penetrate dust around galactic centers. No single color tells the whole story. To understand a black hole, one often needs a symphony of instruments, each hearing a different register of the same cosmic event. The darkness at the center is quiet, but the science around it is richly multi-voiced. 94. Black holes also challenge our emotional sense of scale. A stellar black hole may be only tens of kilometers across, yet weigh more than many suns. A supermassive black hole may span a region larger than planetary orbits and shape the history of a galaxy. Small and large trade places in surprising ways around them. This is part of why they linger so easily in the imagination. They make size, weight, time, and brightness stop meaning what we casually think they mean. Black holes are lessons in humility disguised as astronomical objects. 95. The atoms in your body were forged in ancient stars. Some of the stars that lived before the sun ended as white dwarfs, some as neutron stars, and some as black holes. So even these most mysterious objects belong to the same long chain of cosmic transformation that eventually gave rise to planets, oceans, air, and living things. In that sense, black holes are not separate from us. They are part of the same universe that made us, only arranged differently, under different pressures and different histories. The cosmos is one story told in many forms. 96. There is a poetic contrast in the fact that black holes are invisible, yet so scientifically productive. By studying them, we have learned about relativity, thermodynamics, quantum theory, galaxy evolution, stellar death, magnetic fields, and the structure of spacetime. Darkness, when approached with patience, has turned out to be full of information. Perhaps that is one of the reasons black holes hold such a grip on the human mind. They suggest that absence is not emptiness. Silence is not ignorance. What cannot be seen may still teach. 97. In the unimaginably distant future, after ordinary star formation has largely ceased and galaxies have evolved far beyond their current forms, black holes may be among the last major astrophysical objects left. Some theories of cosmic future describe eras in which black holes dominate the long, dim aftermath of a once brilliant universe. Eventually, if Hawking radiation is correct, even they will evaporate. But that end would come so far beyond all familiar timescales that language almost fails to hold it. Black holes are creatures of the deep future as much as of the dramatic present. 98. If the universe ever reaches such a distant era, the final evaporation of the smallest remaining black holes would release bursts of energy. These would be among the last bright notes in a cosmos grown quiet. It is a strangely moving thought that objects famous for darkness may one day end in flashes. Even here, black holes refuse simple symbolism. They are not only endings, not only silence, not only disappearance. They change form, scale, and meaning depending on the time scale from which they are viewed. 99. Perhaps the most humbling fact about black holes is that they were once considered almost absurd. Even Einstein was uneasy with some of the implications of his own theory. Over time, however, evidence accumulated, mathematics held, observations improved, and the universe kept confirming that black holes are real. Reality is under no obligation to stay within our first intuitions. This is one of the quiet triumphs of science. We allow the world to be stranger than we expected, and in doing so, we draw closer to it. Black holes are not just discoveries about the universe. They are discoveries about how far the human mind can learn to follow truth. 100. And perhaps the gentlest final fact is this: black holes, for all their darkness, have illuminated some of the brightest ideas we possess. They have shown us that space can bend, time can slow, light can be trapped, gravity can sing, and the invisible can shape whole galaxies. By trying to understand what cannot be directly seen, we have learned how to see more deeply. So black holes are not merely cosmic devourers or symbols of loss. They are teachers of scale, patience, and mystery. They stand at the edge of understanding, not as walls, but as invitations. In their silence, they have given science one of its clearest reasons to keep listening. And now our long journey begins to settle. Tonight we drifted through collapsing stars and quiet event horizons, through accretion disks and spinning space-time, through invisible boundaries, gravitational waves, galactic centers, and futures so distant that even galaxies begin to feel temporary. We move through darkness that glows, stillness that twists, and silence that can be heard only by instruments patient enough to listen to space-time itself. Black holes can sound frightening in the bright language of daytime. They are often introduced as cosmic monsters, hungry mouths, or final endings. But here, in the slower language of night, they become something softer and truer. They are not monsters. They are natural structures, born from stars, shaped by gravity, woven into the long architecture of the universe. They do not hate. They do not hunt. They simply are. And maybe that is part of why they feel so calming to think about when the day has been too full. Black holes exist beyond urgency. They move on scales of mass and time that make our own rushing seem small. Around them, the universe follows deep laws with extraordinary patience. Even their violence unfolds across distances and ages that soften into stillness from where we are lying now. Somewhere above you, beyond the clouds, if there are clouds tonight, beyond the moon, beyond the planets, and far beyond the nearest stars, black holes continue their ancient work. Some rest quietly in darkness. Some feed and glow. Some pull stars into bright orbits. Some merge in silence, sending waves across the universe that pass through everything, including us, unnoticed except by the most delicate machines we have ever built. And still, the earth turns. Your room remains here. Your breathing continues. The night holds. So if your thoughts are beginning to loosen now, let them. If the day is still clinging to you, let it grow lighter. If your eyes are heavy, let them close. The universe does not need your attention for the next few hours. It will go on bending light, turning galaxies, and deepening mystery without asking anything more from you tonight. You have traveled far enough for one evening. Rest now, and good night.